let's start. So welcome to the last lecture in this course. We went through a lot in this semester, as you know. We started with the antiquity and the development of logic and geometry. Then we spent a lot of time in the 19th century and also the early 20th century talking about this important shift that took place in mathematics and science. And we learned how this idea of truthfulness of axioms, for example, of geometry or logic, was replaced by the idea of consistency of a system of axioms. Yeah? So in this respect, we distinguish between two traditions. We had logicists and algebraists. And we learned how today we can consider axioms as logical truths within, for example, one axiomatic system, but not in the other. As long as these two systems are axiomatic, the same truths now have different roles. Can be true in one, but not in the another. Yeah? Then we learn about the failure of the Hilbert program and how this led to these theoretical models of computation with Turing and Church. And then we learned about the mathematical basis of computer-aided geometric modeling and also computer graphics. And I suggested to you that the models we use today in architectural modeling are following modeling that is kind of characteristic to this logicist paradigm and based on set theory. As the contrast to that, I introduced you to contemporary information technology, and I suggested that it follows the algebraist legacy, which relies on probabilistic reasoning and not deductive reasoning. And in that light, I introduce you to the modeling with Markov chains, and then I introduce you to a novel conception of space by Riemann, and how all of that together led to development of new theories such as quantum physics, for example. Then, as a contrast to set theoretical model of the world that I showed you before, where we know exactly what we are talking about, where each object is kind of precisely distinguished by nature, I showed you the partition paradigm. And how partition paradigm, which we use in quantum physics, kind of change the assumptions about the objects that we are modeling. Now they can be soft and temporal and do not have to have clear boundaries. And then I described the architectonics of the constitution of such models as something which might be promising to architecture. I assumed that such models would allow us to computationally address architectural questions which we cannot address by the instruments we currently have at our disposal. Then in our last lecture, we were talking about computational models that could be used to implement the models of communication, such as the model of natural communication. And I showed you the algorithm called a self-organizing map, and I show you the different perspectives on how you can use this algorithm. And yeah. What I introduced as a promise was an ability to articulate and recognize certain concepts in the data, which we saw last time. Yeah? And in computer science, this algorithm, SOM, it's often described as a visualization tool, even by the very author of the algorithm. And then on the other side, it is easy to find a very large number of successful applications of this algorithm, which have nothing to do with visualization. For example, nonlinear time series prediction, function approximation, control of dynamical systems, and so on. And then my colleague presented a table with a large index of concepts around this algorithm. And the familiarity of this scheme on the left of the algorithm inspired me to superimpose it on the top of this motivic key from natural communication that you can see on the right. And by checking this reference, which my colleague pointed out, I came to realize that all the improvements and modifications of the algorithm that extended the applicability of this algorithm were in fact modifications on one of these four positions within the key. So the four levels that you can see on the right image here. And what was invariant among all of the improvements was the specific position within the key and the role it takes. Then I showed you that on top of that, I introduced a new key called the coexistence key. And this is a key that generalizes this self-organizing procedure on the basis of models of natural communication and glossematics. And this model relates two domains, as you know from before, A and B, by means of two inverse procedures called generalization and projection. And the domain A, which we start from, is a set of observables or measurements, so-called data. So we have another domain B, which is conjugate to A, which means we can express the things either by A or by B. Yeah? And this level B is a self-referential system of nodes and arrows called a category. And our abstract objects that we are modeling, whatever it is described by the data or measurements which are on the level A. And we know that our data and our measurements probably represent something meaningful, but the semantics, the meaning, is not in the measurements. It's in the some kind of system behind the measurements, which we do not know what it is. Yeah. So what we do, we apply this generalization bridge on the elements of the level A, and then this gives us partition spectrum. So this is this colorful disk. And this means that we now can recognize something from something else in our object, which was in the beginning inaccessible. Yeah? This means we have some information. And we get the information, the price we pay is we lose symmetry. We lose context. And now this cipher that unlocks our domain B is known as a category, and it has more potential than what we had at A, which was just a set. And what we need now is this process of formalization. So how a form arises in domain B, which has no form in the beginning. And in terms of Hjelmslev, the linguist I told you about, the role of this bridge, of this generalization bridge, of this arrow pointing downwards, is to give birth to the form of the domain B, but now in the domain within the to give the form to the domain A within the domain B. Yeah. So then, if we can resolve the problem on the level B, we just need to what we need to do is translate the solution back to A to understand what this solution means. So the second bridge, which points upwards, I call it projection bridge. And now you have the whole path. Start from the level A, go down to the level B, solve the problem on B, and go back to A. So you make a full circle. And this projection bridge, now coming back, closes the path. And we have coexistence between these two levels, so this means we can communicate. And now, to illustrate the potential use of this model in architecture, I want to present you an experiment today. So it's going to be very pragmatic. And the object of my investigation are floor plans, and my goal is to employ them in order to introduce a measure of similarity between architectural spaces. But how to do this? I want this measure to unfold from the representation itself, not to take something else external to it, but to unfold it from itself, so to say. So I will see what I mean by that. So my hypothesis is that we cannot adequately pose this question within our established models because they rely on this pre-given notion of space where we actually take our objects and submerge them in space. So some space is something like a box, and then you put an object in space. This is how we work with our models today. You have a CAD modeler, and then you build an object in it, and it's just submerged. And you can move it around the space, and it changes the coordinates, and so on. Yeah? But my hypothesis is that if you want to speak about similarity in this space, you cannot do it, because you are submerged into it. You need to somehow look at the thing outside of the given space of representation. So you need to construct another level of representation where the same phenomena is represented but in completely different terms. And then we can ask this question once we have this other level. Yeah? Now we need the level B of our schema. Yeah? And I had to show you that this is actually possible to do. And when I was making an experiment, I was thinking, what would be an adequate architectural representation that I could work with? So should I use, for example, vector drawings like CAD drawings, or should I use 3D models? Then what kind of models should I use? Should we use solid models, or should I use surface models? Or maybe I should make physical models and then scan them. Well, I wanted to make a kind of informed decision about it, so I made a list of requirements. What should this representation satisfy so that I can work with it? And this is what I described on the left. So I put to myself certain requirements. I said, representation must give an adequate and comprehensive account of the architectural space, its proportion and function. So I'm interested that I have a kind of accurate representation of space. Okay. Then representation should be standardized and its code and ciphers familiar. So it means it should be something that architects understand, that I understand, so that when I translate it back, that I know what's going on. Yeah. And then I said actual encodings of a large number of buildings in terms of data should be generally available and possible to acquire for the purpose of the experiment. So idea is I need to be able to get that somewhere. Question is, can you get a lot of 3D models of buildings? Yes, but it's more difficult. What format should I use? It's also difficult to make a decision. But then I realized the most adequate representation should be simply an images of floor plans, because internet is full of them. They're all standardized in a way because they're in the same format, JPEG, for example. And yeah, they do show kind of how architectural space should be represented, and it shows the proportion of space, it shows the function, and all of that. Yeah. So, and then I decided to create a kind of simple communication model just to illustrate the thinking. So not to go into too sophisticated models so that I lose everyone in detail. So it's a simple model. But then when I chose to work with floor plans, I had another set of problems. For example, scale. If you have two floor plans in different scale, they're not commensurable, they're not comparable. Because in one, toilet is going to be this big, and the other is going to be this big. And then when you try to compare them, how do you compare them? That's impossible. So the idea is to make that if this is the case, I should have something, I should have kind of, I should have certain aspects of this data set standardized. For example, all the drawings should be in the same scale. But then there's another problem. If you look at the image on the right, you can see that architectural space can be described in many different ways. For example, it can be described for construction, with all the dimensions and everything. Then it can be described as a blueprint. It can be described as, for example, number 3 is from the TV show Friends. It's the 2 apartments that they have. So someone decided to describe it in a certain way. Then on the right, you can see an ad from what's the name? When you rent apartments, like no, the ones where you when you want to rent a flat. What is the platform? Yeah, for example, ImmoScout. So this is how their floor plans look like. Or the image 5 is when you go to an architectural book. This is, for example, how it's represented. So as you can see, it would be very silly to try to compare the blueprint with this apartment from the Friends, because they kind of convey different information. So what I realized, if I want to make this experiment relatively simple, I need to have that standardized too, because these floor plans have different purpose in mind. The one which is made for workers to build a thing, it should not convey the same information as the one which goes into architectural book. I guess you can agree with that. So I decided, for the purpose of experiment, they should all be in the same scale and follow the same conventions of representation, or so-called style of representation. But simply making an experiment is not enough, and I want to kind of give you an idea of what research is about in some way. So imagine you are doing a private research on this topic. What happens is you kind of operate in your private space. But the thing is, once you decide to communicate this, to put it out in the world, you are practically entering the public space. And this public space of research and science is not only public space of today, it's of all times. Yeah? And in public space, you cannot simply do whatever you want without any consequences. You need to behave in a certain way. And this is the same with academic research. So if I have a claim that I have a novel way of comparing architectural space on the basis of representation, then I need to find who tried to do this before and reflect on it, how is now this different. So I need to be polite in this space. I need to relate myself to the others. Yeah? And then for this purpose, I have identified 3 approaches to the problem of similarity of spaces. And they are on 3 different levels of abstraction. And the first one that you see on the left, this models a floor plan as a graph of rooms. So a graph is, you have nodes and you have arrows. And they tell you what is connected to what. So A, B, C. So this example from 1974, what they simply do, this is a kind of set theoretical approach. They say these three images, they are different floor plans, but if you look at the rooms, it's the same, they're the same rooms, and they're connected in the same way. And what they say, the elements we have are bedroom, bathroom, terrace, living room, kitchen, and so on. But it's a set theoretical approach because you kind of already say what you expect to have. So you say something is a living room. You already defined it. It cannot be anything else anymore, you know. It cannot be something between. What is then a living room which has a bed in it? You know, is it still a living room or is it a bedroom with, you know, it's like, in set theoretical approach, you cannot take these hybrids into consideration. Because if you want to make a hybrid, you need to say what it is. It's half bedroom, half living room. So you would need to do things like that, which is very unnatural. Okay. But then the second approach, it's more abstract. And I call it object-oriented approach. So instead of objects that are kind of real objects connected into a network, now we have properties. For example, a property of an element could be, as you can see there, is part of, has boundary, is public, is openables, and so forth. And in the first example, we had actual elements connected in a network. Here, we have properties connected in a network, yeah? And I call this object-oriented approach. And the third approach is, again, another level in abstraction higher. It's about measuring floor plans and describing them as a bundle of different properties. For example, floor plans are described by, for example, measurements that you see also on the list. For example, openness, visibility, distance of any point in the floor plan from the entrance, centrality, traffic volume, so. For my work, I considered, from everything that I saw before, that this third approach is currently what was the state of the art. And this was done actually by Professor Benjamin Dillenberger in his doctoral dissertation. However, these measured properties are still based on a kind of real-world characterization. For example, each floor plan is described, for example, by the distance of any point in the apartment from the entrance. Yeah? And then what this tells you is this floor plan is considered to be a real object, yeah? Real space. And now it's a good time to remind you, why did I present you with this history of mathematics and science? Because remember this story from 19th century. And you know that it brought the foundational crisis. And the crisis was about intuition. So we believed that certain axioms are true because it's self-evident. You cannot see it in any different way. And then this mathematician Lobachevsky, he broke this idea because he created a geometry which was not real in the sense of empirical evidence. So you cannot find this geometry around you, yeah? But it's still a valid construction. So what we learned in the 19th century is that we cannot trust things to be true just because we know them or because they appear to us to be true, you know? So the goal, my goal in the experiments was to stop treating floor plans as real objects that I know, yeah? I need to get rid of my knowledge, and this is difficult. And for that reason, I wanted to go yet to another level of abstraction and then characterize floor plans by means of partition spectra, as it is done in, for example, quantum physics. So first of all, I needed data set should have floor plans in the same scale and have same conventions. So I called the books called Typologie Plus, and this provided me with 188 floor plans. You can see them on the image. And of course, if you have more floor plans, you have better results. But my goal was not to try to make some super optimal solution, but just to show you, to present a certain way of thinking, yeah? And then, in order to make this data set more appropriate for my task, I needed to address certain problems, certain ambiguities, which have to do with this certain representation that we have seen. For example, if the two walls, if we represented if we want to represent wall with two lines, then this is fine for us humans, because when we see an image, we kind of can understand what this means. But computationally speaking, it is very difficult to treat that as an obstacle in space. I mean, walls surely are obstacles in space, yeah? So let's look at the image on the left, for example, top part. So look at this floor plan. So the walls are described with two lines. So now imagine that I take a cut with this red boundary, and I extract this cut on the right. So I then end up I can potentially end up with elements that only have one line representing the wall, yeah? Because the other line is cut from the drawing. So if this happens, then I cannot even think that this is an obstacle in space, because it's only one line. So even if I tell computer, look for two lines, now it's gone, yeah? So now you have no idea how thick that wall might be. So what you can do to kind of help in this situation is to fill the walls with black pixels. Because now, you can now instruct the computer to consider a certain stretch of black pixels, and you say this is an obstacle in space, yeah? So then I fill them with black. And the second thing is rotation. If you have randomly rotated floor plans, this also can be a potential problem, because it is not standardized what a rotation means. So what I did is I kind of transformed image into outline, which you see in the number on the image of the right, number 2. Then I extracted lines. This is number 3. And then I realized that certain lines have certain angle. And there are not so many angles in the image. There are maybe 5, 6 angles. And then certain lines are distributed with certain angles. And then I simply counted which cluster of angles has the most lines. And this cluster, I said this is the most dominant angle. And if this dominant angle was, for example, 60 degrees, what I would do is I would simply rotate the image by minus 60 degrees. And then I will get the image on the 4. So in this way, it is not a perfect way to do this, but it doesn't matter. The only thing is that all the floor plans should be treated the same way. This means to have things done consistently, yeah? So then I got this. So it's the same 188 floor plans, but now you have walls filled with black pixels, and they are all rotated according to the same principle. So now this is my data set. This is what I start working with. And now, again, I go to this image, because this is how I'm going to approach modeling. So what does this mean? So my data set is 180 images that you've seen. I need to consider all 188 of them together as a kind of black box, indiscrete partition, something that I don't know what it is. I need to forget what they are, what I know about them, yeah? So in this way, I think of these 188 images as this black disk there. I have no idea what it is inside, yeah? So then if I wish to recognize something, I need to get the partition spectrum. So this is the colorful disk in the middle. I need to recognize something there, yeah? How do I do that? So the answer is in the right drawing. I'm currently in the domain A, so I need to translate it to some domain B, which will give me partition spectrum, which will give me the colorful image. And for that, I need to take this arrow pointing down, which is the generalization procedure. And as I described later, we can use self-organizing map for this purpose, as to use it as this procedure, yeah? And then this representation that we get with SOM is in spectral domain, not in geometry anymore. And now, these problems in space that we had before, they do not longer exist. We are in a different space. We are in a different domain even, not just space. So now, if we find something in this domain B, we need to translate it back to A, and for that we use this projection bridge, yeah? So when you do that, then you end up with the image on the bottom, yeah? Bottom of the left drawing. So you understand the whole idea. You make this circle. And by making the circle, you can come from something which you have no idea what it is to some distinctions, and then once you want to actualize distinctions, because they are virtual, then you get back and project, and you get certain objects. So these certain objects should give you the meaning of what you learned in the domain B, yeah? Okay, but now to get this partition spectrum, this requires you to partition the object. But the funny thing is there is no established way how to do this. And even less in architecture. How should you partition floor plans? No one knows, yeah? But I need to do it. So it was up to me to discover what you can do and to test it. Does this work well? So first of all, I realized that I already did a certain partition. What was it? I already had 188 images separated so that each image is one floor plan. So somehow, from all possible floor plans, imagine that I had all possible floor plans, I took 188 and I already put them in certain separate images. Okay, so this is one level of partition. This is what I realized. But then, what I needed to do, I then needed to further partition each floor plan. Yeah. So I needed to forget what is the meaning of the elements inside. You know, in each floor plan, you see some familiar elements there. You can see a bathtub, you can see a door, you know them. But I said, I cannot know that. I do not want to know that, what it is. I need to treat it as if I have no idea what it is. So what I did, I simply divided each floor plan into a number of parts, as you can see on the image. And then I divide in each image in parts in such a way that this collection of parts covers the whole image entirely. Yeah? This is what you see in the middle image. And then select, according to the selected size of the parts, if you increase them over a certain limit, then you will see overlapping parts. So certain part of the space can be described like this, without any overlapping. Yeah? Everything fits here. But if you take larger parts, what can happen is that this is then one part, the second part, and third part. Yeah. So now there is part of space which is described by all three. Yeah, and also then do it here. So now these 6 images, they overlap, or you can make an even greater overlapping. Yeah, depends what you want. But this actually, doing this, proved to enhance the models, to make the model better, because it introduced a larger number of elements and greater overall variability. It included all the possible cases, not just specific cases. It included things which we would never consider to be elements. And this, I knew then that I was on the right path when I realized that. So now, when you do this, look what you get. So you take the image on the left and partition it. On the left, on the central image, you see when you have a minimal overlapping, then you have 108 parts from the left floor plan. But then you increase the overlapping with the same size of the parts, you get 432 parts, which you see on the right. Yeah? And I realized the more parts you have, it's better. But then you can even further increase that. Apply something called rotation transformation group, which is a very simple thing actually, as you can see on the image. Why do I do that? This comes from an assumption that floor plans are not always orthogonal, of course. So you can have certain part exist like this in a floor plan or exist like this, yeah? The same part. And you do not know what are you going to encounter in the data. So what you can do is rotate a floor plan and then do the cutting again. And then you end up with more parts. So then if you do it, if, for example, angle of rotation is 15 degrees, then you get 24 elements from one element. So you get much more elements. Yeah? And then when you extract everything, here you can see only 20,000 parts in one image. But I had more than 500,000. Yeah? So what you get here from all these parts is kind of entropic state, like white noise. Yeah? It doesn't tell you anything about floor plans anymore. But if you zoom still, you can recognize some familiar parts there, yeah? So our object is kind of almost a black box, but still not completely a black box. Now we got to an interesting part where I can show you why geometry is not a good representation medium for asking certain questions in architecture, yeah? So look at this image. Depending on how you would cut this image, one and the same element can be found in different positions. For example, look at the rectangles on the top and in the middle. Yeah, these are the same. So if you look at them, each of them contains an element which I might assume that is a column, but in principle I don't want to know what it is. I assume it's a column, but this column is now in different regions of this cut. So what does this mean geometrically? Literally geometrically. If you know how pixels are counted, you know that they are counted in a row. And then, for example, if it's a white pixel, it's 0. And if it's a black pixel, it's 1. Yeah? So now imagine this part. Column is here. And here, column is here. So if you make a stretch of pixels, and you will realize that coordinates of this pixel will be, if this is the system, relevant system, low in x and low in y and low in x, relatively low. While here, it is low of kind of far in x and far in y, in respect to this local coordinate system. So in terms of geometry, strictly speaking, these two parts are different because they have different position in space. They occupy different space, yeah? Would you agree? In geometry, this is different. But what we know but we do not only look at things as humans geometrically. We look at topologically, we look harmonically. We know that this is the same element. It's just somewhere else. And if you want to think about this cell here, we know that we have the same element in the cell, yeah? And it's the same with walls, which you can see also in the image. So you have this wall, and this wall. They are also different because they have different coordinates. They take the different part of the space. But now, even more complicated things is this corner. You know that this is the same corner. It's just mirrored. But it has the same thickness, has everything the same. In terms of geometry, this is different. So this is important to realize. This is why you cannot do this problem in geometry. You cannot solve it. Because in geometry, everything which has different coordinates is different. Yeah? So my assumption is whatever is in these parts that we get is the same thing. Yeah? These two should be the same, these two should be the same, these two should be the same. But this is easier said than done. This is easy for us humans, but how can you translate this to code? Now I want to take you really step by step to understand. Of course, this is a very easy example. What we can do as a solution is to transfer geometrical domain into harmonic domain. What does this mean? So it means from geometry, from coordinates into frequencies. Yeah? So I created something called translation and mirroring invariance bridge, which is a very complicated name for a very simple algorithm, which converts parts into frequencies. So what you do is you scan each floor plan part, as you can see in the image in the center. First, scan it in horizontal dimension. So you scan it line by line, from top to bottom, yeah? From left to right. You scan it. And then you are going through the white pixels, which means empty space, for example. And black pixel means obstacle. Once you see an obstacle, you start measuring. You scan and measure. Once you come to the end of the obstacle, you said, I registered an obstacle which is 30 pixels wide. Okay. What you do, you put it on the list on the right. You just take the number and put it on the list. You continue scanning. So every time you see an obstacle, as you can see on this image, I don't know if you see, there are red points and blue points. Red points mean start scanning, blue points mean end scanning. And you simply take these values and put it in a list. So you just measure the frequency of obstacles in each direction, yeah? And this is the result. So this, you have this part, and this is, for example, only horizontal scanning. So I scan each row, so 150 pixels, I scan 150 times, and I get these numbers on the left. So these two tables that you have here, these two lists of numbers, they're the same values. What's the difference? The difference is that the one on the right is sorted from the lowest to the highest. And already you can see some kind of a spectrum. What would be a spectrum here? You can see that there is a lot of walls with thickness 1 pixel and a lot of walls with 2, and this takes almost the half of the spectrum. So you can generally see that in this image there are a lot of thin lines, for example. And then there is a lot of lines of a certain thickness, yeah? So this is called an algebraic spectrum, or you can think of it like that. And now you can represent this same thing in another way, yeah? So horizontal scanning, so first let's see this upper row. The image on the left is horizontal scanning, and as we scan it, we put it in a list. So simply instead of writing a number, we can visualize it by just plotting it. Yeah, so 30 pixels, 50 pixels, 100 pixels, 1 pixel, 1 pixel, 3 pixels, 40 pixels, 100 pixels, and so on, yeah? So you can put it in a list. And then what you can do, you can also sort this list from the smallest to the bigger ones, so that the largest ones are on the right, yeah? So top one is for the horizontal, bottom one is from the vertical scanning. And now what is this thing on the right? This thing on the right is called a Yeah, it's a bar chart, but it's a histogram, which means you take these values that you have here and you say, what are the standard ranges? For example, this would be the range of 0 to 10. Then this would be the range of 10 to 20, 20 to 50, 50 to 100, 100, 150. Now I'm doing it randomly. And then just see how many you have inside. For example, you have 3, you have 10, you have 15 elements here. So you distribute it within ranges, yeah? And I did 10 ranges, 10 characteristic ranges of stretches of pixels in horizontal and 10 in the vertical. So then each floor plan part gets these 2 histograms, yeah? Blue and red one. So here what you see is, I don't know, 3, 4, 5, 6, 7, 63, I guess, floor plan parts, now shown as frequencies, yeah? Now this is a harmonic spectrum. Each floor plan is represented by a blue histogram, which shows the distribution of obstacles in horizontal direction, and by red histogram that shows the distribution of obstacles in vertical direction, yeah? And now, all of our floor plan parts, all of these little images, 500,000 of them, they are not images anymore, yeah? We cannot visualize them. They're just some list of frequencies. And now, our abstract floor plan objects, so all of the floor plans, they are now truly a black box to us. We simply do not know what our data is. We, as humans, we cannot see it anymore, yeah? We lost it. And this is exactly where I want to be. This is where I need to be to model in this way, yeah? And then what I do, as you remember, I use this bridge, which is a generalization bridge, and I apply it to the set of 500,000 frequency signatures, yeah, instead of 500,000 of images. And this was a self-organizing map, and I organize it in a map which has 100 cells, so 10 by 10. And this is done in a toroidal lattice. So as you know, these elements are connected. If you connect them in a certain way, then you get a torus. And then after the learning is done, then this thing becomes stable on the right, yeah? And then if we take a differential view that I showed you last time with so-called Ulch matrix to show it like a kind of terrain of similarities that I showed you last time with these gray things, gray maps, this we can think about as a partition spectrum. And now we can think about each cell as a virtual distinction. This comes now from the model of natural communication. Each cell of this spectrum, we can now think of it as a virtual distinction, yeah? So as you can see, this red image, it has 20 values. These are 20 frequency values, yeah? But they are not 20 frequency values of any specific part. They are kind of abstract 20 values. They are 20 values which are a prototype of something, but we do not know what yet, because we need to actualize it to know what it is, yeah? So we need to go back. So this is our solution, but we do not know what it means. We have no idea, yeah? Because these are some frequencies in a spectrum. In order to, because we have them virtual now, we need to decide that we agree with this, and we need to actualize these distinctions to see what they mean. This is this step. So each of these distinctions in itself meaningless, but it is relatable with each of our floor plan parts, because they are constituted by the same cipher. As I told you, each floor plan part is a vector, you know from last time, with 20 dimensions. 1, 2, 3, 20, yeah? So it represents a point of space in 20-dimensional space. So now we have 500,000 points in 20-dimensional space, and we have these 100 virtual distinctions also in 20-dimensional space. We need to see which one of these floor plan parts is closest to each one of these parts on the left, yeah? So then each virtual distinction, each cell now attracts certain parts, like a magnet, yeah? Because these are the ones closest to it, because they have similar frequency signature, yeah? So each of these virtual distinctions, which are in green, represents a unique set of actual distinctions, which you see in these with these images with indexes, for example, 1, 7, 7, 3, 6, 2. For example, as you can see, 1, 7, the red dot which attracts 1, 7, which has coordinates 1, 7, attracts nothing, attracts empty space, yeah? While, for example, 7, 3 attracts some certain parts, yeah? But I do not know what these parts are, nor I want to know, because this object is unknown to me, after all, yeah? I take it as something that I don't know what it is, yeah? I approach it like quantum physicists approach modeling, searching for an electron, yeah? So I don't know what it is. I know its frequency signature, and I know where to locate them, yeah? So as you can see, all of these parts attract different actual distinctions. So now I translated it back. So I now have 100 distinct classes of floor plan parts, and I can put them in one image. Because now that I put it back with projection bridge, now I know what virtual distinctions, what do they attract in the real data. And I can visualize it now, yeah? So I have something interesting now. The question is, can we use this somehow to describe floor plans? How do we get from these to floor plans? So what we can do, we can symbolize these classes of virtual distinctions. And from the perspective of Hemsler that I told you before, proper name to call this, according to him, would be figura. But metaphorically speaking, we can also think about these distinctions as an alphabet. This is what alphabet really is. Also in writing, ABC. Yeah, this is what Horstadt always shows. You have this, means nothing, yeah? This, you put this, means nothing. You put this, it's an ant. You know, you add the third, it's an ant. You remove this, you put A, it's art. All three letters don't mean anything, but in context, they mean something. So, can we think of floor plans in the same way? Maybe these symbols that I found do not mean anything in isolation, but as a text, they could be floor plans, yeah? It's a text written in this weird alphabet. So, what I did, I instituted 100 symbols, and I called them, I didn't want to say A, B, C, D, or because there is no simple, I don't have enough symbols, so I called them S00 to S99, yeah? So this is 100 of them. So I want to use this alphabet now to describe any possible floor plan that is created with the same conventions that I started with. And now I come to the pinnacle of this whole course. How do we describe a single floor plan? Symbolically, on the level B. In terms of the level B. Back on level A, but in terms of level B, yeah? So, first, we divide it into a number of parts, yeah? Then, we calculate the frequency signature of each of the obtained parts, and then we present this to our code book, which is associated with an alphabet. Yeah, this is the thing on the bottom, which you see. Now, each part on the left, that is extracted from the left, there will be a single virtual distinction out of 100 on the bottom that is metrically closest to it. Yeah? And since each of the distinctions is associated with a character, as you know, we take this corresponding character and then associate it with each of the parts. And then we repeat this procedure until all of the parts on the left are associated with a single character. So what we get as a result is a space of a floor plan which is described symbolically. Yeah? We get a text from a floor plan, but text in an alphabet that we do not know yet. And this is how a newly obtained symbolic representation of the floor plan looks like, yeah? The same floor plan is now in text. And if you would like, we can also overlap these two conjugate representations in a single image. And then you get something like this. Of course, as an image, this is not very interesting, maybe. You've seen a lot of parametric models which have crazy geometries on the screen, and you say, wow, what is this? But just think about what this means. I think it's quite interesting. So let's look some more examples. So as you can see, I talked about S17. S17 always represents part of the empty space of a floor plan. And I never instructed computer that I even know what empty space is. I completely did not suggest that empty space exists. Yeah? Yet, it's characterized in my floor plans. Okay. Now, at this point, what we achieved is that every floor plan that we have, every floor plan we can give to the computer, as long as it has the same conventions and same scale, can be described not only on the level of floor plans, but in 2 conjugate levels or more, if you wish, regardless of the geometry of the floor plan. Yeah? So we abstracted from geometry. We do not care. Any floor plan will work. So if we are able to do this, we have established coexistence between the 2 levels of our model. What does this mean? By means of this injunction, which is these 2 bridges pointing in the same direction, between the encoding and the decoding process, we can consider any change in any of the levels, top or bottom one, within the corresponding conjugate level. So we can see a change on the bottom level as a change in the top one, and vice versa. And once we achieve this, then the question is, so we have, if this is possible, then we have established communication between 2 levels of our model. This is what it means to have a communication model. Yeah, so you have communication between 2 separate domains. One is geometrical, one is symbolical, but they can talk to each other. Yeah, a symbolic domain on the bottom is talking about the floor plans in its own terms, not any external reference, in its own terms, from itself. Yeah. Then, once we have this, the question is, can we now establish a notion of similarity between floor plans on symbolic basis? Can we now see how there are similar texts? And if you remember, we can do this because we learned about Markov models. This is what we did examples with it. If we have a certain text, we learn how to create a Markov model of it. Yeah? How to get the probabilities that next to one symbol, there will be another one. So we can do this. Of course, you do not have to use Markov models. You can use, for example, recurrent neural networks that will be even more efficient. But I did Markov chains on purpose. And then from these 100 virtual distinctions, this alphabet of 100 characters, this simply means that I have 100 Markov states, and I need to calculate the possibility of transitions from each character to its neighbor. And that's it. Then, once this is done, then we can use these probability values that we get, now these arrows that we got from Markov models, to characterize each floor plan. So now frequency probabilities between characters now become our new vectors. Yeah. So now these are transition probabilities between characters. Yeah. So now they will be probabilities from each character to each other character, from 0 to 1. And now they will have 100 dimensions, 1 to 100. So now each floor plan has 100 dimension vector of probabilities from each character to each other. And now I can make another self-organizing map, another generalization procedure, take 188 floor plans on any number we have, and see how they are similar according to these probabilities. So this is another level of abstraction yet. Yeah? And you get something like that on that image. Now this is a partition spectrum which is in topological space. Yeah? And now if you want to know how similar floor plan are to each other, you need to count topological distance between each part to its neighbor. Yeah? So it's a topological distance between the cells of the image. Yeah? For example, you have these 2 floor plans, you want to know what is their topological distance. You simply need to count the minimal number of steps between any 2 blocks that contain floor plans. Yeah? And with this, I conclude the experiment. And now, I want to reflect a little bit about this whole course. What was this whole thing about? And yeah, you know already everything, but I just want to kind of summarize. And you know, the way we think about these objects all around us, both kind of objects in general, or when we speak about certain specific objects in our programs. This, how we speak about them, relies very much on our intuitions, yeah? And intuition is always there to kind of help us to make sense of things. And then the sense that we have from things gives us stability. Gives us stability in whenever we need it, yeah? And today's information technology takes these things that we like to keep stable and disrupt them, completely disrupt them. This is what's happening today. And it doesn't seem to provide a new stability. It looks like that, at least, yeah? So we are kind of overwhelmed with all this information coming, and everywhere we look, infinity. Infinity here, infinity there. Infinity of images, infinity of photographs, infinity of floor plans, infinity of architectural offices, everywhere you look. And each object, then infinite complexity. And then you have this infinity, and if you have anything to symbolize it with, like we had with, for example, square root of 2, which is incommensurable in a Pythagorean triangle. If this is 1 and this is 1, this is square root of 2. It's incommensurable. It's an infinite sequence of numbers. How can you represent it? You know, you lose your ground. What happens now is that we have these square roots of 2 in our digital domain. So it's something that we don't know what to do. All we need to do is symbolize it. We need a symbol for that. And then learn how to work with symbols such as square root of 2. Therefore, this infinity that is in front of us appears very scary. And then, if we don't want this infinity to hurt us, then we get engaged. And how we get engaged? We start trusting our senses even more and our intuition. And as you know, in 2017, people made a conference of Flat Earthers Society. So they gathered around and they say, yeah, the Earth is flat, let's make a conference. We should talk how Earth is flat, because that's a common sense, yeah? So here, I don't want to offer you a solution. I just want to give you a different instrument to look at this thing, at this scary thing, yeah? So it's free to use, but it also comes with a price, and this price might appear too high. And because it requires us to give up our keeper of stability. It asks for us to give up on sense. But how to give up on sense? By affirming all possible senses at the same time, just as we do in quantum physics, yeah? We need to accept that infinity really is everywhere we look at, and every object contains it. And then if you see that, today's world of information will not be world of infinite complexity, it will be a world of infinite giving. It will be a world that gives, and what it gives cannot be exhausted. Yeah? So just accept what it gives this world as it is today, and say thank you. And this is a metaphor that I made when you take a bunch of different floor plans and discretize them into an enormous number of arbitrary and meaningless cuts. Yeah? So from the perspective of sense, when you cut them all, you are indeed left with no sense at all. Yeah? But then once you have them all cut and meaningless, and a lot of them, yeah, then something interesting can happen from this situation. This is what I wanted to show you. Now you start playing. You take these pieces of nothing and all, you start measuring them, you put them in constellations, you combine them, you connect them, you make them dance for you or whatever, yeah? And soon enough, they start talking, as you can see. They start organizing themselves. And then they start talking to you too. And this is how you can create meaning from something which has no sense, yeah? And today, we call this digital. Now I would like to finish with this table of distinctions that I identified during my work. And I believe that the notions that we have on the right column, this is something which is very relevant to our current body of thinking. And yeah, I use this as a personal compass. You can use it too if you find it meaningful. Of course, my idea is to communicate this thing to you. And of course, architecture is where my interest in architectonics comes from. So I just believe that we have a special ability as an architects. We are able to abstract things on a certain level of things on reality. We are able to integrate them on a higher level, which is an abstract level, which is not concrete always. At the end, we will put it back to concrete objects. But we do operate on a certain abstract level where we consider things outside of their original domain. This is what we architects do. And this can be quite precious to understand and to deal with this complex concept that I went through today. And what we do best as architects is really an integration of these seemingly unrelatable things. This is what we do the best. But what I want to suggest with this course, that now we might be able to do it on a more higher level of abstraction. And this is what the message of this course is. So yeah, thanks for for joining. That's it. So I suggest we close the recording now and let's